How do I know if my pandas will be slow? Today, we're going to discuss a lot of the optimizations and fast paths that you can access in pandas to make sure that your data processing pipelines, queries, and everything computational will be fast. And in order to reason about how these things take place, we'll dive a little bit under the hood of pandas and talk about some of its original design by Wes in 2008 and a lot of the changes that have taken place since then. We will be talking a little bit about pandas internals, how things are laid out in memory, and how this might differ from things that you might experience in, say, SQL. And of course, in order to do that, I will start by sharing my screen. So behind me, you'll see my screen. I'll, of course, hide here. And I did want to say that you'll find the notes for all of these up right after this session concludes. So the first thing that I want to talk about, objects and strings. When working with data frames, we are constantly working with textual-based data, whether that is a bunch of short strings, maybe representing tickers or IDs, or very long textual data, maybe you're working with passages, tweets, or even posts from other social media sites. We are constantly working with strings, and it's very important to work efficiently with strings. But in order to think about how we can work efficiently with strings, we need to think about how strings might fit into memory. And the very standard two approaches were introduced to us right by SQL way back. And we can think of these in terms of a dichotomy. Typically, if we want to store a lot of strings into an array, we will either take a fixed width string approach or a variable width approach. And in order to represent this, I'm going to use a little bit of SQL here. And we'll go ahead and create our very own table. And I'm going to create tables in this, or two columns in this single table. One will be of a varchar type, and the other will be of a char type. And now the difference between these is varchar stands for variable characters. So this is going to store strings that are up to 20 bytes in memory, whereas the char field is a fixed width string, and so this will ensure that every string is exactly 20 in length. And so let's go ahead, we'll fix this up because these titles are backwards, but all we're going to do here is we're just going to insert a bunch of randomly generated characters that are generated here on the Python level. And you can see from these characters, all I'm doing is I'm just grabbing a bunch of random text. They are going to innately be of variable length between length, 2 and 10 characters each. We're going to generate 100 of these, insert those into our table that we just created, and then I'm going to pull those back out. So I'm going to insert a bunch of text into my SQL table, and then I'm going to pull them back out, and I'll use a data frame just to represent them. But what I want you to take a look at here is once I pull these out, note that the characters in the char field actually have what I referred to as a fixed width, meaning if they were not 20 characters, they will be padded with white space until they hit 20 characters. You can think, if I store a bunch of these in a contiguous array, or a continuous memory layout, I can look up any one of these strings very quickly. I know that the second string is going to be exactly 20 bytes after the first string. I know that the third string is going to be 40 bytes after the first string. And so I can use this idea that we see all the time in NumPy and all array logic of how to have a very fast constant time lookup. Now with our varchar type, we do not have that extra white space, that fixed width padding. And so we can think that I might not be able to index into a structure like this as quickly. I would need some way of storing either an offset or the length of a given string. But what I do save on is memory. And so if memory is my limiting factor here, the varchar type will be very nice. And the reason that, we don't see differences between these two at, the API layer, the superficial layer, is that SQL by default will always or often strip off this white space before performing any operations. And so you can see here in my SQL statement, I'm just grabbing out that character column, the varchar column, and I'm testing whether they are equal to each other. And you can see, even though there's this white space here, well, these are in fact equal to each other. SQL is simply removing that white space before performing the comparison. And then obviously I'm pulling these all into a pandas data frame just to present them to you. And so this is very important because if we think about these two types of memory layouts, these are the two types of memory layouts that we often see when using strings. And so for our fixed character, we know the exact amount of space that every entry is going to take up, and we can use this to our advantage in order to perform fast lookups at the cost, of a little bit of extra memory. Or if we're talking millions of records, it could be a lot of bit of extra memory, so this is a big sacrifice. For our varchar, or variable character type, we know that each entry will take up a dynamic amount of space with an apparent maximum, In SQL, I put a maximum of 20 bytes per one of those strings. This will reduce in slower lookups, but it will have the advantage of a nicely reduced memory footprint. We're going to have a much denser representation of our strings in this case. Now, there are other character types, or text types, I should say, in SQL. The text type specifically is used for storing very large amounts of text. And so if you're familiar, with something with the text schema, the text type there, that's what we're looking for. It's very similar to varchar, except it leverages a little bit more of the newer features of SQL to let us work with extremely long strings in SQL. So when should you use either? Well, I would use a character string if you know that all of your data are going to be maybe a uniform length. This is very common, If I'm working with tickers, you might have width of 4 here. And so you could very well store these into a fixed width string just like that. And you would have the advantage, of fast filtering and fast indexing operations, as well as memory footprint that's not going to grow out of scale with the data. But oftentimes we want to have preventative measures, especially when creating tables. And that's, well, what if I need to insert a 5-character width string or a 6-character width string? Do I simply pad this out to some maybe unknowable future? Or do I simply just go with varchar and say, my life is just simpler this way? I'll leave that up to you because it is a domain-specific problem. If you know for a fact, say I'm working with tickers, no ticker is going to be more than 4 bytes, so I can go ahead and use a fixed width string there and be fine. But for our variable character type, well, for this, if you have things like IDs, things that might differ in their length, and they should be stored as a string, and I will stand by this, IDs should be stored as strings, well, then you might want the varchar type because you'll have an apparent maximum, No ID should exceed a length of, say, 100 bytes, but I don't want to hurt myself or sacrifice any memory if just in case, some of those IDs happen to be under that apparent maximum. And so the varchar type is useful for more kind of dynamic textual data, but I wouldn't use it for very long textual data, That's when I would use an actual text type. So now that we've talked a little bit about SQL, let's talk about, well, what does Python, NumPy, and pandas do, and how can we use this knowledge to our advantage to predict when pandas is going to be slow? And so I've taken that same approach of generating a bunch of different length strings here. And you can see in Python, if I just store all of these in a list, well, we have a simple list of strings. But let's talk about how the list is laid out in memory. We know that each one of these strings is just a Python object. And so if I want to index into these, I can simply grab the 0th, grab the 1st, the 2nd, the 3rd, and it looks that element up. The great thing about the Python list is it has a constant time lookup because secretly in the Python list, all we're actually looking at here is a contiguous array of pointers that then point to the actual Python object. And this means I can have a dynamic size of that Python object without actually impacting the size of my list of pointers there. But this level of indirection, or this addition of indirection, does cost us at the performance level. But as we'll see, it doesn't hurt us that much. And when I say at the performance level, if I wanted to perform a uniform action across all of these strings, well, I need to visit each of these elements in the list. First, I would need to know that if they're all strings, and then I would need to perform an action after visiting each of them. And I would need to do this at the Python level, meaning I would need to use a Python for loop and Python function calls, which can be a little slow. Now, the string methods, right, will be implemented not in Python itself, but rather in C. And so the string methods will be fast with the overhead, right, of the initial function call. Let's talk about NumPy now. If I take this list of strings that we just saw here in Python and convert it to a NumPy and D array, well, I get something that's represented very much the same, especially when I print it out. But what I can actually do here is I can inspect, right, the data type and some other features of this list or of this array. The NumPy data types, you'll see that I have less than U10. This is that varchar, or sorry, this is that fixed width character data type. And I can prove that to you. This is saying that all of the strings here are actually a fixed width up to 10, right? 10 bytes maximum. And so if I actually look at this, I can, since this is a NumPy and D array, I can view this, right, with a different data type, and I can say, well, show me every single byte as its own element or own entry into the array. And what NumPy is implicitly doing, right, it's trimming off that white space in the exact same way that we saw SQL do. And so when I print this out now, with this changed view into my NumPy and D array, well, you can see that I actually have 10 slots per entry, and each of these slots will be padded with white space, or with empty space, I should say, until it hits, right, those 10 bytes total. This means my NumPy and D array can have a constant time lookup of, well, any given byte, which is pretty cool, but also, right, if I keep it as the original data type or the original view, I can have a constant time lookup of any given string here. Now, this isn't terribly useful. I don't know many use cases where inserting a bunch of strings into NumPy is going to have a fantastic performance, especially over what Python already offers with its list. But let's move on and see how pandas stores this data, or works with this data, I should say. So when we take a pandas series and we insert a bunch of characters into it, you see one very interesting thing, and that is the data type here. If you're not familiar with pandas, pandas uses an object data type, or the O, when it cannot do anything special with the data that you have supplied it. Meaning, in this case, this is just a bunch of Python strings, and I might as well be better off with just a Python list, because every time that I look up or grab a single item out of this series, it has to check, okay, this is a Py object, okay, what is it? Oh, it's a string. The object data type is used typically for heterogeneous data, or for strings in this case. Now, this is even true if I were to say, take this array that has that fixed width type and pass this into my series constructor, where pandas will typically try to preserve NumPy data types, you'll see that it does not, in fact, preserve this NumPy data type of the fixed width character. And so even here, right, when I construct directly from an array that has that fixed width at less than U10 for Unicode text, we still end up getting an object data type back. Pandas decided quite early on that there is not much use for supporting explicit fixed width strings, because the nature of working with data frames is that you are constantly changing them and transforming them. And so they said, well, the dynamically allocated strings in the Python list is going to be good enough for the majority of our use cases. If you really want fixed width strings, please go use NumPy. We're not going to add a convenience layer on top of it. Now, this has changed slightly in recent history with the release of, I want to say, Pandas 1.3. So this was still quite some time ago. They introduced initial support for the PyArrow backend. And so oftentimes, instead of seeing that D type of object, or that D type of O, you'll now start seeing a D type of string, or specifically string array backed by a PyArrow array. And effectively, PyArrow, it's not a re-implementation of NumPy at all, but the whole point of PyArrow is to have a lower level library that data frame-like libraries like Pandas can support and take full leverage of. It turns out that the things that people want to do with data frames are quite different than the things that people want to do with multi-dimensional arrays. And so they created, or Wes went off and created, right, PyArrow or Arrow in order to have better support for this. Now, the main difference between this string backend ran by PyArrow and what we've seen in NumPy with the fixed width is that this string backend is actually very similar to the varchar that we saw in SQL. The string backend is storing all of these strings in a single contiguous array, and then it has a secondary array. You'll often see this with Pandas data type extensions, that it's some type of array backed with some metadata. And so the original characters are all stored in a single contiguous array in memory layout. So you would actually see this value immediately adjacent to this value, immediately adjacent to this value, and so on and so forth. But the secondary array is providing an offset. And so the offset for this first entry would be, in this case, 0. The offset for this second entry, well, it's however many bytes are in this first entry. And this way, we can still support a constant time lookup because we can just skip n number of bytes in order to advance to the first, second, third, fourth, and so on elements, while still having what works as an incredibly compact memory layout. Meaning that if I were to inspect the memory usage of these individual entities, let's do, I believe it's memory usage deep equals true. And we'll do the same thing on this PyArrow backed array here. And let's see, D type, we'll get rid of that. You can see that the PyArrow backed string ends up using less memory because this up here, right, has all of the overhead of every single individual Py object. And so we'll end up using the PyArrow string backend for most operations. It's going to have a more compact memory layout, so a reduced memory footprint, and it's also going to be slightly faster. But let's talk about why. Why would this PyArrow implementation be faster for strings specifically? So here I'm going to test all three of these approaches. I'm going to have my list, which is my characters. I'm going to have a NumPy and D array fixed with NumPy and D array called ARR, a series of objects or a series with an object D type called S, and then S2, which will be my PyArrow implementation. Let's go ahead and test all of these against each other. What we're going to be testing. NumPy has a bunch of vectorized operations specifically for working with string arrays. It's from the numpy.char. So if you ever see this import from NumPy here, import char, you actually have vectorized operations for character strings. Now, depending on the operation you're doing, right, this vectorized operation could be no better than just using a Python for loop and calling specific string methods. But let's take a look. Up top, we have our NumPy and D array, and the operation that we're going to do here is to transform every single character from its lowercase representation to its uppercase representation. NumPy, we're leveraging the char upper method. In Pandas, we can use the .string accessor with the upper method as well, and we can repeat that same thing using the PyArrow backed, right, series 2. And then in Python, we're just going to do a list comprehension here full of values. So let's go ahead and we'll run this snippet here. And you can see that just right out the gate, Pandas with a PyArrow backed, right, string array is going to be our fastest option. And let's think about why this might be. NumPy will need to examine every element and then uppercase all of the actual characters while also operating on, right, those white space characters that end up doing nothing. So it's wasting a lot of effort. Our series backed with Python objects, well, it's going to be at its best no better than a Python for loop with something like a list comprehension. And then it has the overhead of reconstituting that series as well. And so it's going to have to visit every single Python object, ask it, what are you? Are you a string? Okay, let's call your .upper method in that case, and then reconstitute that series. And so we see not great performance here. PyArrow, since it has that very dense memory layout of all of my string characters, it knows the data type of every single element in this series, and it can visit them all without even looking at the offsets. It just has this dense representation of every single byte, and it can then call upper on every single byte very quickly. Our list comprehension, now this is fun because this is actually faster than both NumPy and our Pandas object type, and all I'm doing is calling a list comprehension. So This is run on Python 3.11, so we do have a little bit of the speedups from the Faster Python project. And just as a reminder, I'm looking at 1 million strings here. So I'm telling you right now that a list comprehension performing string operations is faster than using numpy.char or using a pandas object string method accessor for working with strings. And so don't ever throw out, right, Python list comprehensions, especially when you're performing string operations.